Okay, so today what we are going to do is we are going to look at approximating derivatives, right. So far we have looked at approximating functions, right, and we have seen there are lots of ways by which we can approximate functions. All I have done by way of either box functions, Haar functions, hat functions, right, all of cubics, quadratics, cubic splines, quadratics and so on is just one class. There are many ways by which you can, right, approximate functions and represent them on the computer, which is the most important part that we are interested in. Now we saw in the last class that if you had a function f of x and you wanted to find out what was its value at f of x plus delta x, that we could use Taylor series, right, we could use Taylor series to write f of x plus delta x in terms of f of x. Okay, so for the sake of this discussion, like I did earlier, I will say h is approximately xi plus 1 minus xi. I know I have introduced delta x because that is what you are used to seeing in your Taylor series formulas and so on, right. So I will write this as f of x plus h is f of x plus h times the derivative f prime of x plus h squared by 2 factorial by 2, second derivative of x and so on 3 factorial, third derivative. Is that fine? So I am just writing a Taylor series expansion of f at x plus h expanded about the point x, right, that is usually what we call it. And it is possible for us, one thing that we saw was it was possible for us to approximate x at f at x plus h in terms of these terms. The more information that you have, the more terms that you can add. So if you know the first derivative, you can get a representation whose error is of the order of h squared and so on, right. The other possibility that we saw was that we can actually use this to extract out the first derivative, that is f prime of x can be written as, solving for f prime, f of x plus h minus f of x divided by h. Then we have to take all of these infinite number of terms to the other side, and what will that give us? Plus excuse me, minus h by 2 f double prime of x minus h squared by 3 factorial, which is 6, the third derivative of x and so on. Okay. If you go back, if you think about one of the definitions at least that you have seen of the getting the derivative, of actually calculating the derivative, right, from first principles using limits, you would have seen that f of x plus h minus f of x divided by h, right, limit h going to 0, right, would be the definition of the derivative, and all of these terms will go to 0 and you will get the derivative. So that is an infinite process, right, it is a limiting process, it is an infinite process. We do not go through the infinite process, so we stay with the finite process, and therefore this is called the finite difference. Okay, so we have a finite difference approximation for the first derivative. I will truncate the series at that point. I will truncate that series at that point. This error that you see here, all the terms that I have truncated, is called the truncation error. Truncation error. And the order of the truncation error is indicated typically by the leading term, which is minus h by 2, the second derivative of x. Is that fine? Okay. So the representation that we have for the derivative f prime of x, right, is f of x plus h minus f of x divided by h. If I am going to truncate it, then I have to replace this, it is really more of an approximation rather than, right, rather than being exact. So you could call it f prime we can indicate an h up there, prime of x, the h indicating that, right, equals, and as I told you earlier, I will use this h to indicate that it is an approximation, and after a point maybe I will drop it where there is clarity that I am actually talking about an approximation. So this is f of x plus h minus f of x divided by h, and the truncation error is minus h by 2 second derivative of x. What is the nature of the truncation error? In the limit h goes to 0, as h gets smaller and smaller, the truncation error is going to go to 0 in a linear fashion, okay. So the convergence is basically first order convergence, okay. For what polynomial, what degree polynomial is the truncation error 0? For a function that is linear, right, for a function that is linear, So this sounds like the hat function, Remember what was the derivative of the hat function on the interval xi minus 1 or xi plus 1? So that was fi minus 1 divided by h, it's the same thing, okay. So we are essentially representing, in a sense we are representing the function when we do this, when we go through this process, we are representing the function using hat functions, linear interpolants, okay. So and of course we will ask ourselves the question, can we do better than this, and we can obviously do better than this because we know that we can represent the function using quadratics, cubics and so on. Because this function, because this approximation involves x plus h and x, and the derivative is at x, right, we are using a point that is ahead, so I will again, so if this is xi, this is xi plus 1, right. So if I call this point, the function value here is fi, so I am saying that f prime, I have already dropped the h to indicate, so I know it is f prime at the point I is fi plus 1 minus fi divided by h. Since I am using a point that is ahead, this is called a forward difference. This difference is called a forward difference. Right. So it is a forward difference approximation Is that fine? So if you can have a forward difference, the natural question that you have is, can we have a backward difference? So in order to do that, just like we did earlier, we say f of x minus h is f of x, we just follow that process, same process, plus h times f prime of x plus h squared by 2 factorial second derivative of x plus cube 3 factorial. I am sorry, I am making a mistake here. I have to pay attention. Thank you very much. H cube f triple prime of x and so on. The sign change is important, right? So, and therefore solving f prime, I will just write it in the same notation, f prime at I is f at I minus f at I minus 1 divided by h. And what is the truncation error? H by 2 times f double prime at I. This is minus h by 2, this is plus h by 2. Is that fine? Minus h by 2 and plus h by 2, the signs are opposite. This is called a backward difference. Backward difference. So that is a backward difference approximation. Is that okay? Okay, so we have a forward difference approximation, we have a backward difference approximation. Look at this. So at the same, across the same interval, I have these two across, let me not go there, just a second. So I have I minus 1, I plus 1. So I have one representation for f prime I, which is a forward difference, one approximation for the f prime, which is forward difference, right, at the point I, which equals fi plus 1 minus fi divided by h. I am just rewriting that, minus h by 2 f double prime of x. Then I have another approximation backward, I will just write back at I, which is fi minus fi minus 1 by h, and the error here, truncation error here is okay. Is it possible for me to get a better approximation if I give you these two to get a better approximation? It looks like if I add this estimate and that estimate, this error will just cancel. You understand? It looks like if I add this, so if I take the average of these two, so this is just by way of suggestion, just from observation, f prime some approx I is, what is the average of these two? fi plus 1, the minus fi and plus fi will cancel, minus fi minus 1 divided by 2h. This goes away, so I will have to go back and recalculate my truncation error. So what would be my truncation error? What is my truncation error going to be like? I have a minus h cubed by 3 factorial, which is plus h cubed by truncation error is 2h squared by 3 factorial, which of course has a we can just do it. There is a minus h squared by there is a minus h squared by 6 here, okay, and what are we going to get here? You have a plus h squared by 6. Anyway, what we will do is we will do this the legal way. Let me not. So you can try going through this process. You will see that we will actually go through this the legal straightforward fashion instead of this intuitive. So here all I am saying is, if I look at this, this gives me a clue. So I have a forward difference approximation, I have a backward difference approximation in this fashion, and it turns out that these terms cancel. Okay. So when I say let us go about this legal way, what I am saying is, if you want to find the truncation error, there is only one way to do it. You have to get the series and actually do the truncation error. So we have to get it from Taylor series. Okay. So let us get back to the first one. We get it from Taylor series. So it involves the points x plus h and x minus h. So I will rewrite my Taylor series for x minus h. F of x minus h is f of x minus h times f prime of x plus h squared by 2 factorial f double prime of x minus h cubed by 3 factorial f triple prime of x, and so on. Is that okay, everyone? So what I am going to do now, I want to solve. So this is how you would do it, right? So please do not go around taking averages and all. That was just a question to lead us intuitively to the spot. So this is how you would do it. What do I want from these two equations? I want to get f prime of x, that is my objective. I want to solve for f prime of x, So which means that from the first equation if I subtract the second equation I will get 2 f prime of x, 2 f prime of x is f of x plus h minus f of x minus h divided by, well, so I will remove the 2 f prime of 2h, so I am dividing through by 2h. What happens to this term? It cancels. There are 2 of these but I divide by the 2, okay, and therefore I get, and we have to make sure that the sign is right. So you have a minus h squared by 6 f third derivative of x and so on and other terms. That would be the truncation error. Okay. So in this particular case as h goes to 0 we converge quadratically, okay, the error goes to 0 quadratically, h squared. And what about the polynomial that we are using? That is also quadratic, that is also quadratic, okay, that is also, by chance it happens that it is also quadratic, it is also a second degree polynomial. We can represent a second degree polynomial, we use a second degree polynomial for f, this term will be 0 and f prime will get the right answer. Is that fine? Okay. So essentially we are using parabolics to represent the f in this case, right, though we have not actually constructed the quadratic, right, all we have is those points. If you go back and try to find the coefficients, right, for the quadratics and cubics, if you go back, right, we did, you have done, as I say, I repeat, we have done hat functions, quadratics, cubics. I have not used quadratics and cubics to represent functions, right. I would suggest that you try it. If you go back and try to do it, when you look at, you will get a system of equations for the coefficients, and when you look at the system of equations for the coefficients and solve for the coefficient, you will be surprised that, you shouldn't be surprised that you will get terms like this. Just try it out, right. There is a reason why I ask you to do it, right? If you have done it, this should look familiar, right, you should, there's supposed to be an aha moment for you saying that, I have seen this, right, when I did the quadratic I got exactly the same expression, okay. So there is a connection between this and the quadratic, the coefficients of the quadratic, okay. Well, so this is what we have. Let me make an observation here and then we will see what is it that I am going to choose an interval to see what it is that we have. This is I plus 1. So I can have some function in between, right, there is some function that I am sampling, this happens to be fi, that happens to be fi plus 1. What I am doing is, if I look at fi plus 1 minus fi divided by h, so that you get a clear idea as to what it is that we are doing here, right, fi plus 1 minus fi divided by h, this length is h, right, just for clarity. I am actually calculating the slope of that line, I am calculating the slope of that line. If I were to take the slope of that line and assign it and assume that it is the derivative at the point I would be doing forward difference, right, and the error that we have, the truncation error that we have is minus h by 2 f double prime at I. If I were to take the same slope, the same number, the actual number that you calculated, if I were to take the same slope and assign it as a derivative at this point at I plus 1, right, then I would have backward difference, the same number, right, the same actual number that you calculate is a backward difference, and the truncation error would be h by 2 f double prime, be careful with this, I plus 1, okay. And interestingly, If I take that and assume that it is the derivative at some midpoint, right, derivative at a midpoint, now my h is not the same h there, this is right, but it is still, I mean so 2h actually becomes h in that formula, so it is the same expression, you just have to be careful with the truncation error, okay. Then the truncation error, if I take it as a central difference for this, would turn out to be h squared by 24 third derivative, you can think about that 24, right, and this is at some intermediate point, we do not know what is that value, but it is some intermediate point I plus half, I will just call it I plus half, it is the midpoint. The same number right is first order approximation there, forward difference, backward difference, this is called central difference, okay. So central difference, the same number, central difference is a better approximation. So that basically, actually if you think about it, this should remind you of mean value theorem, right. Mean value theorem simply says that if you are going on a continuous path, if you are walking on a continuous path, right, from one point to another point, if you are walking on a continuous path from one point to another point, then somewhere in between in that trajectory, what does mean value theorem say? You are walking parallel to the line joining those 2 points. If you start at a point and go to another point, you understand, if you start at a point and go to another point, it does not matter, you have following a continuous path, somewhere along the line you must have been walking along the line joining those 2 points, that is all mean value theorem says. It does not say where, that is our problem, okay, it does not say where. So this line joining them, the function is tangent to it at some point, the problem is we do not know where, if you give me the point at which it is tangent, then I have the exact derivative at that point, somewhere in between it is the exact derivative. Here it is an approximation which is first order, here it is an approximation which is first order, in between it is an approximation which is second order, and at some unknown point it is an exact representation. Somewhere in between for a continuous function, fi plus 1 minus fi divided by h is the derivative, is that clear, okay. And it is the fact that we do not know it that gives us this truncation error, the fact that we do not know at what point it is the tangent that gives us this truncation error. So it is possible for us to calculate the derivative, to approximate the derivative, to estimate the derivative at any given point, it is possible for us to estimate the derivative at any given point using forward differences, central differences, backward differences, and the forward difference, backward difference and central difference have the appropriate truncation errors, okay, associated truncation errors, right. So and each one of them you will see as we go along, there is a reason why you would use one or the other, right, okay. Are there any questions? So then there comes the natural next question, if I could use x plus h and x minus h to get a second order, right, we are a little greedy, why do not I get, how is it possible for me to use a third equation and get one more, right, a higher order approximation, is it possible for me to add one more term, one more equation to that and get a higher order approximation, and it is possible, okay. So I will go back here. So what happens is something, no, I want to solve for f prime, okay. So just to be careful, I will add one more term, and you allow me to change the notation slightly, h to the 4 factorial f fourth derivative at I, and plus h to the 4th by 4 factorial f fourth derivative at I. Is that okay? Fine. So I am going to go with this subscript I, though I have left the other terms as x. I am not going to rewrite the rest of those equations, but you allow me to change to this notation, so that f of you want to take one behind, one ahead, we have to decide where to take it. If I take I minus 2, that corresponds to f of x minus 2h, okay. F of y minus 2 is f of y minus 2h, second derivative, first derivative at I, I make a lot of mistakes, plus 4h squared by 2, second derivative at I, minus 8h cube by 6, third derivative at I, plus 16 by 24, that is 4 factorial, fourth derivative at I, and so on. It should be possible now for us to, what shall we do? How can we go about this? What we want, our objective is to make sure that we retain the first derivative term, the f prime term, we retain the f prime term, okay. So when we had two equations, we essentially eliminated the f of x and retained this term, okay, and eliminated the f double prime, the f double prime term, right. We do not mind having the f of x, actually the f of x got eliminated as a, right, that was just one of those side things that happened. What we really want to do is get rid of this. Now in this case I want to get rid of the third derivative term also. Am I making sense? It is clear. So you have basically 3 equations and I want to get f prime of I at I out of it. How can we do this? What's the deal? How should we do this? I have a double prime here, I have a double prime here, okay. So I want to knock this out. What do I get here? So if I take this equation and this equation, so this is basically 2h squared, or 4 by 2 is fine. So I need to multiply the first equation, if I multiply this equation by 4, and subtract say the second equation from the first equation, right, that should get me something. So if I take this and multiply it by 4 and subtract this equation from there, what am I going to get? 4 fi minus 1 minus fi minus 2 equals 4 fi minus 1 minus fi minus 2 equals 3 fi and I have a minus and plus minus 2, no not minus 2, minus 2 h f prime at I, then minus, I say minus but I write plus, okay, minus 2 h f prime at I plus this term and that term are going to cancel, that is the whole objective. Then I have 4 of these, I have 8 of those, right. I have 4 of these, I have 8 of those, plus 4 by 6 2/3 h cube f triple prime at I. Then what else? I want to retain the fourth derivative. I have added the fourth derivative because it is likely that I suspect that my truncation error is going to be like the fourth derivative, right. So there are 4 of these and 16 of these, right, there are 4 of these and 16 of these, minus 12 by 24 fourth derivative of I, so on, fine. h power 4, most important, h power 4, okay. So that is taking these two, and of course earlier we had knocked out the h squared term by subtracting these from each other, which gave me fi plus 1 minus fi minus 1 equals, I will just repeat that, no fi's plus 2h f prime at I, this quadratic term cancels out, plus 2h cubed by 6 f triple prime at I, and what happens to the fourth derivative? The fourth derivative cancels, fourth derivative cancel, plus 0, fourth derivative cancels, okay. Let us move on. What does this give me? What do I want to do now? I have a 2h f prime I here which I want to retain, but I have a third derivative term here that I want to eliminate. I have a third derivative term here that I want to eliminate. So if I multiply the second equation by 2, if I were to multiply this equation by 2, if I were to multiply that equation by 2 and then do what? Subtract one from the other, okay. So from maybe the second equation, from this equation I subtract that equation, so I get 2 times fi plus 1 minus fi minus 1 minus 4 times fi minus 1 minus fi minus 2, 4 times, oops, I made a mistake, I have to be a bit careful here, 4 times fi minus 2 minus fi minus 1 minus fi minus 2. This gives me minus 3 fi plus, there is a 2h f prime and a 4h f prime, 6 h f prime at I. What else? The triple prime goes away and we have multiplied this, so it will be plus 1 by 2 h to the 4th or that is plus fi minus 2, h to the 4th derivative at I. Is that okay? Fine. So what does this work out to? I want to solve for the f prime, so I will take everything else over to the other side, I will swap the equations around because I want the f prime. So f prime at I equals I have a 2 fi plus 1 minus 2 fi minus 1, let me leave the 6h here, I do not skip any steps, minus 4 fi minus 1 plus fi minus 2 minus 3 fi plus 3 fi plus 1 half h fourth derivative at I minus. So clearly I am going to make a lot of sign errors today, okay. This gives me where it doesn't add up. Okay, 2 Fi plus 1 plus 3 Fi minus 6 Fi minus 1 divided by 6H minus 1 by 12 H2 H cubed F to the 4th derivative I. Yeah, Fi, I'm sorry, I shouldn't say Fi, my Fi plus 1. Where did I get an Fi plus 1? Fi plus 1, Fi minus 1, Fi minus 2. Fi minus 2 minus H cubed by 12 F to the 4th derivative. Let me add them up and the check that I am performing, I am performing a test here, it may not be obvious. The test that I am performing is I am adding up the coefficients in the numerator, and in fact they do add up to 0. Okay, in fact they do add up to 0. So here you have some mechanism by which we have got something that has third order, converges as third order, okay, and the representation is third order cubic. Is that fine? Are there any questions? Okay, right. So it is possible, so one thing is for the representation of f prime at x, right, can be represented or approximated. I will slowly switch from representing on the computer to approximating on the computer, represented / approximated, right, using various points, the sample values at various grid points. So you can use Fi, I plus 1, I plus 2, I minus 2 and so on, can be represented to apparently any order that we seek. Any order, it's just a matter of adding points. As you add points, as you add more and more points, right, as you add more and more points. So if you have I plus 1, I minus 1, I minus 2, then apparently you can get, right, very high order, higher order, as high an order as you want. So it's possible that you can actually get higher and higher order representations or approximations. Okay, so right now I just make that as a broad statement. What we need to do is we need to find out, and we have this truncation error, everything seems fine, right, everything seems fine, but you have to be a bit careful. Okay, so what I do is I will give you an assignment. I ask you to try this out and see what you get. So we can use this representation that we have to check whether we are actually getting a derivative. So pick a function. Since we are talking about trig functions in the last class, I will use sin x. So you try out sine of x plus h or x plus delta x or whatever minus sine of x divided by h. Calculate this. Okay. So this is a candidate derivative. This is a candidate derivative for sine. Let's assume it's forward differences. So at x, right. So this is a candidate derivative f prime at x. You also know that the derivative is actually cosine x. Pick a value of x, right, pick a value of x, say x equals pi by 4, and pick a value of h, say h is pi by 4, okay, and evaluate this for different values of h. Evaluate this for different values of h, and what I want you to do is look at cosine of x minus f prime of x divided by cosine of x you can take either, right, take the modulus if you want to keep it positive, and what is this? This is some kind of a relative error. Fine. Okay, so far so good. Now this is what I want you to try to do. You try to make h smaller and smaller. So in your program you keep halving the value of h. So you say h is 0.5 times h in your program. You keep halving the value of h and keep calculating this relative error, and I want you to plot on a log-log plot. On a log-log plot I want you to plot the relative error versus h. Is that okay? Is that fine? Okay. So now that that's clear, you tell me what you expect. Now that the assignment is clear, what do you expect? I want you to try it for different schemes, that is I want you to do it for forward difference, backward difference, central difference. What is it that you expect? Remember, h grows larger in this direction. H grows larger in this direction, that means you are starting somewhere here, that is pi by 4, and you are going to work your way towards 0. Okay. How many times are you going to divide by 2? How many times are you going to, for how many values of h are you going to try this? H, well, whether h should be below machine epsilon or whatever it is, you figure out whether it should, does it have to be below machine epsilon, let it go, you do it, just see what happens, right. So what is it that you expect, say for a first order scheme, for a forward difference, this is forward difference, what is it that you expect, what do you expect the graph to look like? You expect a linear curve like that, something like that. Try it out and see what you get, right. And if it is second order, no, you have to be careful, it is second order, it is still going to be linear, this was a 45-degree line, second order will be, you expect a steeper line, you go through the origin, I do not get it, some problem, or maybe it starts somewhere else. I do not know if I am making sense. You are taking log on both sides, you have log error, relative error equals whatever, look at the truncation error, work this out, you try to work it out, we will get back, we will take a look at it, try to work it out, okay, try to work it out, and as I warned you before, always some little trap in something that I ask you to do, so keep your eyes open, okay. So keep having this, maybe try 64 times possibly, right. That is a lot, right, or 50 times, try halving it 50 times, okay, that should not get you into trouble, try halving it 50 times, try it for float and double, float double, you can try long double, okay, try a combination and see what happens, is that fine, okay, right. So let's get back to this. As it turns out, we are able to get derivatives of derivatives of various orders, approximations to a derivative first derivative of various orders. So can we get second derivatives, right? So we look at these two equations, and in fact it turns out we can get a second derivative if you just add the two equations. It is clear now that these terms will cancel. So we have f of x plus h, which is f of I plus 1, plus f of x minus h, which is f of I minus 1, as 2 times f of x, which is f of I, fi. This term cancels, plus h squared by 2 goes away, f double prime at I, which is what we want. This term cancels, leaving us 2 of these plus 1 by 12 h to the fourth derivative at I, and there are higher order terms. We can solve for the second derivative, and therefore the second derivative at I equals fi plus 1 minus 2 fi plus fi minus 1 divided by h squared, and the truncation error is minus 1 by 12 h squared fourth derivative at I. Okay, that is the truncation error. Is that fine? I wanted to, so it's pretty obvious actually. One, I wanted to do it today because it's straightforward. The expression is here, we can just subtract, get the second derivative. It's possible to get the second derivatives in terms of I plus 1, I minus 1 and so on. I also wanted to do it because I wanted to make one thing clear. What is the rate at which the truncation error goes to 0? H squared, it's quadratic, it's second order, right? It's second order. What is the polynomial that we can, for which we can get the answer? That's cubic, right? So I don't want you to get in your mind that the function representation is quadratic, convergence is quadratic, right? That was only for first derivatives. When you go to second derivatives, the error term converges as h squared, but the order of the representation of the function, you understand, the order of the representation, right, is the fourth derivative, and therefore you can represent a cubic exactly. Does that make sense, right? So only if you plug in a fourth degree polynomial will this be non-zero. Okay, so even for a third degree polynomial it's going to work, but this convergence is second degree, second order. Okay, right? Just because for the first derivative approximations they seem to match, I don't want you to get in your mind they matched because we were dividing by h, but here we are dividing by h squared, and I suspect looking at this that maybe for third derivatives we end up dividing by h cube. Okay, so that is one thing to remember. So you have a h squared order of convergence, representation is cubic for the function. Is that fine? Okay, so it's clear using the values of the function at various locations that we can actually approximate derivatives, right? So we are now in a position to actually approximate differential equations. Is that fine? Right? So we are now, so once we are able to approximate functions, once we are able to approximate derivatives, we are in a position to approximate differential equations. We can approximate the differential equations and actually represent our functions on the computer and systematically hunt for the solution. Okay, so this we will do in the next class. What we are going to do is we will look at a equation in 2 dimensions. So all my derivations are in 1D. I am going to look at the equations in 2D, but before I finish I just want to emphasize some terms that I am using. So these are, if I minus 1, I plus 1, I plus 2 and so on, you will see me refer to this whole interval being broken up into a mesh or a grid. I will explain these terms in more detail later, and these points I will typically refer to them as grid points, but you may hear people referring to them as nodes. Okay, right? So I will typically refer to them as grid points. So given function values at grid points, we are able to represent functions we are able to represent derivatives, and therefore we will be able to represent on that mesh a differential equation, right, because we are able to represent derivatives, and also extract out a solution which we are able to represent on that mesh. Is that fine? Okay, so that is our objective next class. Fine, thank you.